Which kind of solar meets my needs? In this lesson, we're going to discuss different system types and start to understand more details about the applications for either ourselves or our clients and the major components that make up these different system configurations. We're really looking at the electrical architecture, if you will, of the system to better understand how to make selections based on our needs, our location, and what sort of power we're trying to provide. So to begin this, we want to think about what are my needs? What are the applications that I'm looking for to utilize solar? And what sort of equipment would go into those various applications? The first thing we want to think about here is what we would call off-grid systems. Off-grid systems are going to be in remote areas or disconnected from the grid in some way. Usually this is a PV system that's not connected to the utility. When we say off-grid, we mean it's an independent power system. And because it's independent, we must provide for power for all connected loads. If we're providing an independent power supply, we have to run everything within our design from this off-grid system. If we're grid connected, then we're going to be integrated with the utility. The reason we do this is it's a more affordable power. PV systems can sell electricity into the utility grid, and systems like this don't have to have energy storage. Because we don't have energy storage, we can keep our system installation costs lower and our equipment costs lower. And often these systems can have a quicker return on investment because of the lower cost. Of course, return on investment always needs to be weighed with the other system types as well. But a grid connected system is usually a more simple electrical system with less components, and therefore it makes it a little bit easier when we're in the right applications where we have a stable electrical grid. The other type we want to think about is backup power. Do I need backup power? Backup power gives us a reliable power source. PV systems can sell electricity to the utility grid or operate in a standalone mode. Those are things that are able to be programmed within the system depending on the equipment we buy. And because this system has energy storage, it's able to provide that kind of hybrid approach to either grid connected or backup and standby energy when we need it. As we begin, we want to understand the main components. What are the things that are going to make up our power system? So let's discuss the main components of a solar electric system. So when we start to utilize them in some coming diagrams, we can better understand what their purpose is. So when we think about generation of electricity, we can use things like PV arrays or motor generators to generate electricity. And so those are going to be our sources of electrical generation that we're going to look at based on our application. We also have things like inverters. They give us conversion of electricity. So conversion means we're going to turn DC to AC. And as we remember, there's a lot of different inverters out there that are designed for different applications. And that's what we want to start thinking more about now. Regulation of power. This is a charge controller. And anytime we have battery banks in our system, we need to add a charge controller or a charge regulator in order to regulate the electricity from the solar into the battery. Of course, the battery bank or our storage device, if we need storage, then we'll utilize a battery system in order to give us that energy storage. But we may not. There's a lot of applications for systems without energy storage that may meet our needs just perfectly without a battery, and that we'll assess more in the coming slides. And then, of course, everything is designed around consumption. What am I trying to run? How long am I trying to run it? What's the weather and the local conditions that could affect the various loads that we're trying to operate? So those are our main components, and we're going to look at some of the different applications and how we would utilize these components in different system designs. Now, the first system we're going to look at is an off-grid system, which would be a small DC-only system. And so if we look at this basic layout, now to think about DC-only systems, if we discuss the application, this could be charging anything, charging small batteries things like mobile phones, radios, flashlights, any sort of basic charging needs we could do with a system like this. We could run lights for any either street light or interior lighting or any lighting that we need in a off-grid standalone situation. And then we could also do things like refrigeration with a system like this. And so if we look at our layout, we have the generation of DC electricity from our PV array. So the sun shines on the PV array and we create DC electricity. That energy then flows into our charge controller, where we regulate the charging of the battery. And so the charge controller is going to manage the solar array and regulate battery charging. Then when we leave the charge regulator or charge controller, we go into our storage side, so our battery bank. So that's how we're going to store energy so we can utilize it either when there's not enough sun or at nighttime or anything where the load is larger than the solar production. And then, of course, that's going to go to consumption. And in this example, we're looking at DC-only applications, so a simple DC lighting system. So when the sun shines, we charge the battery bank, and ideally we would get that battery bank full every day. We use the PV array, the charge controller, and the battery bank to create and store energy. Then when the sun goes down, we can use that battery bank and our energy storage to run our electric lighting. Very basic system, and this could be a lot of different sizes and scales, but most of the time this is looking for small DC only systems because we don't have an inverter in here. Now, one of the downsides to a really simple system like this, if we leave the consumption on too much, we could actually drain this battery down to a point where we could do damage to our battery. Sometimes we may want to add extra protection in there in the form of what we call a load controller. We want to protect the batteries from overcharge, but also from over discharge. So here we're going to look at a slightly different version of that same system, an off-grid small DC system. But the difference is we're now using a charge controller with what we call an integrated load controller. It's a very simple charge controller, but it has the ability to also control the electrical loads and manage the in and out of the battery charging. So if we step through this diagram, the sun hits the PV array, we generate DC electricity. DC electricity goes into the charge controller, and then the charge controller connects to the battery bank. So the charge controller is able to control the charging of the battery to make sure that when the battery is full, we turn off the solar and we prevent the battery from overcharge or damage. Now at nighttime, we run our electrical loads, our DC loads, and because we're running it through an integrated charge controller and load controller, then we can also protect the battery to make sure we don't over discharge it. So as the battery gets empty, once it goes down low enough, the load controller will turn off the lighting to protect the battery bank itself. These are great systems for charging any of the devices that we've discussed, and basic simple lighting and refrigeration systems as well. So just a couple different ways that we can go about operating small DC electrical loads. Now, if we say, okay, we want to now run electrical loads with AC electrical consumption, then once we need AC electrical output or products, we're going to integrate an inverter into the system. So everything is the same as the previous systems. We generate DC electricity from our PV array. We run it through a charge controller. We can store that energy in our battery bank. And then we can also take that energy either from the battery or the solar or both at the same time. And we can run an inverter that turns our DC electricity into AC electricity to run to our AC distribution or AC service panel for our AC electrical consumption. Now, this is a basic inverter, and a basic inverter is a one-way device of DC in and AC out. And so this is how we can have an AC system But the one thing with this is it's an AC system with no generator backup. So we're dependent with a system like this on how much sun we have, how big our PV array is, how big our battery bank is, and how many AC electrical loads do we have in the system. So something like this may have to be monitored and managed a little more closely because we don't have a backup source. Now, if we want to add a backup source into a system like this, we need to have a slightly different inverter. So now this inverter is what we're calling an inverter charger. The inverter charger means we have the ability to not only do a DC to AC conversion, but we can go AC to DC from something like a generator, a motor generator, and we can use that to charge our battery bank. So in a normal operation here, sun shines on the PV array, we make DC electricity, we send that out of the charge controller to the battery bank or the inverter, and the inverter sends it to the AC loads. So we're generating, regulating, storing, converting, and then consuming energy. A system like this could be used for running homes or businesses or even industrial applications. This can be built on a lot of different sizes and scales. So it really just depends on proper sizing of the system to meet the needs of the client. Now, with this inverter charger, we now have this inverter that's able to take the generator input and charge the battery bank up if the sun's not shining. So if we don't have enough sun, we can turn on the generator, keep the batteries full, and then have 100% electricity supplied to our AC loads, whether the sun's shining or not. And no matter how many cloudy days we have, as long as we have the generator as a backup system, we'll always have power. Now, a more advanced inverter charger, depending on the quality and the complexity of this particular inverter charger, we can also do things with the generators like automatic generator start and generator control systems if the inverter and the generator are capable of having those sorts of functions. And many of them are. We just need to know if we intend to work with a generator in a system like this, we want to select the right generator and the right inverter, not only sized to match my needs, but it also needs to have these additional features of generator control, which allows a more seamless integration and a more autonomous system that doesn't have to have the generator started or monitored by a person, but we can program it to operate automatically. And that gives us a much more reliable and independent power system that someone doesn't have to pay very close attention to all the time to make sure that we have power 100%. Now, a couple more off-grid applications that are very common around the world is water pumping. And water pumping with solar continues to grow every year as a great way to utilize solar energy all over the place. And we can run water pumps to do things like agriculture and farms. We can run our homes, or we can even do big systems that will run towns and villages. There's a couple different ways to pump water with solar. In this example, we're using a DC water pumping system. And a DC water pumping system, when the sun shines, we're going to take the PV array, generate DC electricity, and run a DC pump in order to pump water. Now, because a system like this has no energy storage, it's just solar to the pump directly, the amount of water pumped is going to be directly proportional to the size of the solar array, the size of the pump, and how many hours of sun we have. So when the sun shines, we pump water, and when the sun sets, we stop pumping water. So this will not pump at night because it doesn't have any energy storage. It's just a daytime only system. So if we were going to use it to run our homes, we might need a secondary pump in order to pressurize a system, or we could pump this water to an elevated tank and use things like gravity supplied energy to pressurize the water system so water could be available 24 hours a day. Now, DC water pumping systems are very common and normal out there, usually for smaller applications. As we get into larger applications, we may want to use more of a traditional AC electrical pump system. So what's really amazing is there's some great new products in the market now in order to utilize AC single phase or three-phase pumping systems. This has become much more common on large AC pumps. And so maybe we're going into a larger agricultural application or a village application where we need bigger pumps with higher amounts of horsepower. And an AC pump is more commonly available and usually a lot cheaper at larger sizes than the DC pumping system, just because the number of AC pumps that are produced around the world. So what we can do to run an AC pump with a PV water system is we can buy these special inverters that we call a variable frequency drive inverter. Now, variable frequency drive inverters are really designed specifically for motors and motor control systems. And so this is really what I would almost call like a pump inverter, that it's designed to run a motor and to manage that motor in a special way where we can do it without energy storage, without batteries. And so similar to the DC pump, when the sun shines, we're going to produce electricity. We're going to produce DC electricity from our PV array. We're going to turn that into AC electricity through the variable frequency drive inverter, and then we're going to power an AC pump. Now, just like in the DC pump example, once the sun sets, we're going to stop pumping water. And so the amount of water pumped is going to be based on the size of the array, the size of the inverter, the size of the AC pump, and how sunny of a day we had. Like I mentioned on the other DC pump, if we want to pressurize water at night, we can pump this up a hill to a storage tank or to an elevated tower and use that to gravity feed water for a pressure system. If we wanted to run this type of pump 24 hours a day, then we're going to need to add energy storage like a battery, like we looked at in our previous examples, to allow 24-hour-a-day water pumping. So that's why we need to really assess our needs when we design systems like this to know whether a daytime only pumping system is adequate or whether we need to plan for energy storage in a system like this. Now, we're going to step away from the off-grid market for a minute, and we want to think more about a grid-connected market where we're using AC systems with no battery. And so the difference here is now we're going to take our PV array and we're going to run the DC of that solar array into an inverter. Now, this particular inverter is what's designed to be a utility synchronizing inverter. So it's meant to synchronize with the electrical grid, take the DC in, make a perfect AC waveform that perfectly matches our utility's voltage and frequency. And we need to specify that inverter for that purpose, where it is able to take the solar and export it into the electrical grid and sell excess energy if our utility company allows us to. So if we look through this diagram, we generate with our PV array, we convert DC to AC with our inverter. We also use that inverter to synchronize with an existing AC source like our electrical grid. We push that energy from the solar into our AC electrical service panel, where that's where our electrical loads are. So we can either consume that energy in the home or in the business or in our factory at that point of connection to our AC electrical service. Or if we set this system up this way, we can take that excess energy, if we have it, and we can send energy back in to the utility grid. So we would push all the energy from the solar into the service panel, meet our electrical loads there, and then continue to push excess energy out of the service panel through the meter and onto the utility grid if our utility allows us this type of interconnection and net metering type of system. A system like this does not have energy storage, and so we're not keeping any energy in the building. We're producing everything and either consuming it or exporting it. So you see our arrows from the AC service panel to the utility grid show that they can go both directions. That's because at any given time we could either be exporting or importing electricity depending on the size of the solar, the size of our electrical consumption, and how sunny it is at that given moment. So when the sun shines, we have normal operation, we supply our panel, and we can either export or import at the same time to meet 100% of our AC electrical loads. Now at night, with a system like this, when the sun sets, the PV array stops producing electricity. This inverter shuts off because it doesn't have anything it needs to do because the solar is off as well. And we provide all of our AC electrical service from the utility grid, just like we did previously. Now, as I've mentioned before, a system like this needs to have a stable electrical grid in order to stay interconnected. Because there's no battery, it's not a backup power system. So it needs to be interconnected with the utility grid to operate. If we're in a place with a reliable utility grid, then a system like this may be the cheapest way that we can generate solar electricity and could have the best return on investment because we don't have to buy the additional cost of the energy storage system. But the downfall to a system like this that we must understand, and our clients or customers or homeowners or businesses must understand, is that because this system is utility dependent, then if the utility grid fails, our system doesn't produce any power because it has a safety protection in here where it's designed to never export electricity into a dead utility grid. So that's why we call this a utility interactive or a utility synchronizing system. It is dependent on the utility grid and the solar in order to turn that inverter on and operate normally. Even if the sun is shining and we have sun hitting our PV array, the PV energy is available theoretically, but if the utility is off, this inverter is not going to allow any of that electricity to be exported into the grid as a safety and precautionary system. You could couple this with a backup generator if you wanted to, where the utility grid or the AC service was operated from a generator if you needed that backup power, or you could add a battery backup. But a system like this that doesn't have any energy storage is one of the most common electrical systems for PV out in the world today because it's usually operating at the lowest cost. Now, if we say we want the solar, we want to be able to synchronize with the utility, but sometimes our utility goes out fairly regularly and we need some sort of a backup system. Well, then we can integrate what we call a multi-mode inverter charger. And that multi-mode inverter charger is designed to do a couple of different things. It can synchronize with the utility grid and sell electricity into the electrical grid, just like the previous inverter that we just discussed. It also, being an inverter charger, could take an AC circuit from the utility or an AC supply and charge the battery bank as well. So that battery could be charged from the AC source, which is in this case the utility. The other thing we're going to have in a system like this that's slightly different is we're going to set it up with a backed up AC loads panel. And by a backed up AC loads panel, what we're doing is we are choosing which electrical loads we want to have backed up in case of an outage and which electrical loads we don't. So we're usually going to have two electrical services in a system like this. The main coming from the utility grid will not be backed up when the utility fails, and the backed up load panel will be able to operate when the utility's down. The reason we separate some of those AC loads like that is because the more we choose to back up, the larger the system becomes. The larger the inverter, the larger the battery bank. And so we can back up anything we want. We just need to assess what the costs are. And so if in order to save money on my system, the more I minimize my backup amount, it gives me a way to save on the size of my battery bank and my inverter. So what we might do is put things like that we don't need to have backed up. Maybe, let's say if we're talking about a residential application, if I had an air conditioner or a washing machine or some of the system, larger electrical loads that are maybe less essential, I keep those in my main AC service panel. And then what I choose to put in my backed up loads panel, what most people are looking for are things like lighting. So we can have common area lighting that's always available. People usually want some sort of refrigeration. So we'll put a refrigerator on there and possibly water pumping if we had a water pump system. So we can have refrigeration and water pumping if we want to have that backed up. And a lot of times people want to back up some sort of communication so they can know what's going on in the world if there was a power outage. So that might be things like radios, cell phone charging, TV, internet, things like that are common backed up loads. Now, people often ask, can I back up an air conditioner? Yes, of course you can. You can back up as many as you want. It's just going to affect the price and the sizing of the system. Maybe if you have multiple air conditioners, you back up one in a common area and leave the other air conditioners in the main service panel that's not going to be backed up. If we walk through this system again from the left to the right, similar to the others, we have PV array generates DC electricity, charge controller manages our battery bank, the battery itself is our energy storage system. The multi-mode inverter charger means I can operate grid synchronized and I can sell to the utility grid if I set the programming that way. I can also take an AC circuit from the utility grid and I can charge my battery bank if I need to keep that battery full and ready for an outage at any time. And that multi-mode inverter charger is able to run my backed up loads panel in the event that the utility grid failed. And so it can operate in this, the reason it's called a multi-mode is it can operate grid connected or it can operate like a standalone off-grid system depending on what supplies of electricity are available at any given time. Kind of gives us a more complicated system, but also a lot more capability as well. There's a lot of different inverter chargers that are out there that are capable of doing this in this multi-mode function. And so if this is the sort of system that you're looking for, then you need to specify the type of inverter charger you have or that you need in order to operate the loads that you're trying to run whenever you need them based on your system design.